You are listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on our topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronic What's Up podcast. The world of technology is ever-changing. Wide bandgap power semiconductor devices like Silicon Carbide or SiC-MOSFETs are enjoying growing popularity in many modern power electronic applications like e-mobility and renewable energy. Their extremely fast switching speed capability helps to increase efficiency and reduce the overall size and cost of the system. However, fast switching, together with high operating voltages and increasing switching frequencies, presents important challenges to the gate driver system. Rugged galvanic isolation, compliance with safety standards, control signal noise immunity, and EMI performance, those are just some of the most important aspects that designers need to consider. An optimal design of the isolated auxiliary supply, providing the voltage and current levels to drive the SiC or GaN device, is critical to help the full gate driver system meet the many requirements set by state-of-the-art applications. And today, we're going to explore this design. First, an overview and requirements for gate control of high-voltage SiC and GaN field effect transistor, or FET devices. In applications using SiC or GaN high-voltage semiconductor devices under hard switching operation, galvanic isolation is a common requirement for safety and functional reasons, and depending on the application, a basic or reinforced insulation will be required. The operating voltage, insulation material, pollution degree, and the applicable regulatory standards set the minimum creepage and clearance distances, as well as the dielectric isolation voltage requirement affecting the components placed across the isolation barrier. The high-speed isolated gate driver IC and the transformer in the isolated auxiliary power supply both bridge this isolation barrier, so they have to meet stringent safety and functional requirements. You can find our example of the DC to DC block in Figure 1 attached in this podcast. Some of the latest SiC-MOSFET devices require typical gate voltages of up to 15 volts for full turn on and negative 4 volts for reliable turn off. For a GaN FET, usually about 5 volts and 0 volts are required respectively, although a small negative voltage can also be applied to ensure turn off in presence of excessive gate voltage ringing. You should also note that these values may vary depending on the manufacturer. When we continue looking at Figure 1, we see a half-bridge configuration, and several of these stages are typically required in an inverter circuit to drive AC motors in the kilowatt range. Each SiC or GaN FET would require an independent gate driver stage with its own isolated auxiliary supply. This enables individual control of each SiC or GaN device, and also helps to keep the gate current loop small and local to the device, minimizing the adverse effects of parasitic loop inductance and ground bounce generated during the switching transition. Otherwise, this may cause uncontrolled turn on or off of the MOSFET and thermal issues. Some SiC MOSFETs are designed with an additional low impedance Kelvin source connection for a gate current return path. This connection does not carry the high switching current, so it has a lower interference potential than the source connection, which significantly improves gate driving. When we look at the auxiliary supply, it should be compact with its own output capacitors placed very close to the gate driver and SiC or GaN device to minimize the gate current loop and other parasitic effects. Now we'll discuss the requirements of the isolated gate driver power supply for SiC MOSFETs. Now, at the moment, a large selection of compact, isolated 1 to 2 watt DC to DC converters are on the market. For a SiC MOSFET like the design from Infineon, up to 1 watt power requirement per device can be estimated. Our calculations can be seen in Figure 2 of this podcast. Meanwhile, an application with over 5 kilowatt load power requires the use of either a SiC MOSFET module, like the module from Rome that's 1200 volts and 600 amps, or several discrete SiC MOSFETs in parallel that are current sharing. In a module solution, several semiconductor dies are paralleled to form the final SiC MOSFET. This technique reduces the effective resistance on, but results in a very high total gate charge, which places a high power requirement on the gate driver system power supply. Above 2 watts of power, there's only a very limited selection of off-the-shelf isolated DC to DC converter modules, and despite their convenience, they're often large, weighty, expensive, and with efficiencies lining under 79%. The SiC MOSFET modules that are currently available feature a total gate charge of 3,000 nanocoulombs. With an increase in the switching frequency or load power, 6 to 10 watts of driver system power can be expected for the most demanding present and near future applications. Among the solutions available that actually meet these expectations, one of the best 6-watt isolated converter modules on the market currently has the following specification. An input voltage range between 9 and 18 volts, an output voltage of positive 15 volts and negative 5 volts at 6 watts, a size of 40 by 28 by 9 millimeters, between 76 and 79% efficiency, a parasitic coupling capacitance of 15 picofarads, a weight of 12 grams, and basic insulation for bus voltage of 800 volts. Efficiency, weight, and especially the parasitic coupling capacitance are often critical parameters in high-performance systems, especially at higher switching frequencies of the converters and the resulting very steep switching edges. The harmonics must be capacitively decoupled between the converter output stage gate driver and the system power supply, for example, from the DC to DC converter. The parasitic capacitance between primary and secondary sides is mainly set by the interwinding capacitance of the DC to DC power transformer device. With latest SiC MOSFETs switching at change of internal energy over change in time, slew rates of 100 kilovolts per US 10 picofarads parasitic capacitance across the barrier would cause a peak displacement current of 1 amp, which is coupled by the switching transistor across the isolation barrier. A high dielectric displacement current degrades the insulation barrier in the long run. It disturbs the control signals, and it leads to common mode currents in the corresponding device, which can be seen as typical EMC problems. It is recommended to keep parasitic coupling capacitance in the auxiliary supply below 10 picofarads. Luckily, Worth Electronic has met all these requirements, and we are pleased to present the new optimized solution with a new SiC gate driver power supply reference design. The high-performance bipolar isolated auxiliary power supply design of Worth Electronic features an input voltage range between 9 and 18 volts, an output voltage of bipolar 15 volts negative 4 volts, or unipolar between 15 and 20 volts, power up to 6 watts, peak efficiency of up to 86%, a weight of less than 4 grams, and a size of only 27 by 14 by 14 millimeters, making it over 50% smaller than similar DC to DC converters on the market. In addition to the controller, in this case analog devices, the key component in the design is the new power WE AGDT transformer. A compact EP7 customized package was used and optimized to meet these requirements, including a wide input voltage range between 9 and 36 volts, high saturation current of 4.5 amps, very low interwinding capacitance, 6.8 picofarads, very low leakage inductance for highest efficiency, surface mount, pick and placeable, and a creepage and clearance distance minimum of 5 millimeters. This transformer is also rated for safety standard IEC 62368-1, IEC 61558-2-16, and is AEC Q200 qualified. For more information, a comprehensive reference design document is available for download in this podcast and at Worth Electronic online, along with the corresponding PCB layout design files. It's worth noting that the power capability can be easily scaled to 10 watts with an EP10 transformer core and appropriate uprating of some components. The new WE AGDT gate driver transformer series features 6 different transformers, each of them optimized for different specifications and their own reference design. These transformers offer flexibility, ease of use, and a combination of bipolar and unipolar output voltage rail options, covering the gate driver requirements not only for state-of-the-art SiC-MOSFETs, but also GaN FETs and widespread silicon IGBT and power MOSFET devices. With the new AGDT transformer series, Worth Electronic is demonstrating its innovative strength, addressing future challenges in the field of power electronics. For the first time, the developer has the possibility to easily implement a compact and efficient gate driver supply with up to 6 watts output power capability and top performance. You are listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic tech specialists who are going to shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronic What's Up podcast.